Hello everyone, good afternoon. So I'll talk about our work on string transformations, and also we'll talk about how formal verification is used in industry. So this work is jointly done with Professor Krishna. So I'll first talk about string constraint and the problem of separability for string constraint. Then I'll briefly talk about string transformation, string transducers, because our results uses automata theoretic relations. And then finally, I will talk about formal verification use case in hardware industry. So recently, set 10 SMT solvers are heavily used in industry, and actually it's an active research area in industry as well as academia. So simply, if I take a base case, so consider this Boolean constraint, which says that P and Q or R evaluates to true. This P, Q, R are variables which can take values or true or false Boolean values. So to make this equation to be true, there can be multiple satisfying assignment. One of them is listed here. That is, if we take P to be true, Q to be true, and R to be false, this whole equation will become true. So this is about Boolean constraint. If we extend this theory with strings, so it is called string constraint. Simple example I'll give here first. Then we'll look at formal definition. This is a very basic string constraint which says x equal to ay. Here x and y, these are unknowns or variables, and a is a constant. If we assign x to be ab and y to be b, we can say that this constraint is satisfied. And another kind of string constraint can be membership constraint. That is, variable x belongs to some language or regular expression a star b star. So if we take x to be ab or a ba or any word which starts with a and has b as a subword in suffix, then it will satisfy the constraint. So this string constraint is actually being used in industry. AWS uses string constraint to assure their customers that their access policies are what is intended to be. That is not the person who does not have access should not get an access. So for that, they are using the string constraint. They are encoding their access policies into string constraint and passing it to solver. It's inductively defined using atomic constraints. One kind of atomic constraint is membership constraint, what we have seen as an example. X belongs to some regular language L. So for example, x belongs to AB star. AB star is a regular language and it can have multiple satisfying assignment, like AB is a satisfying assignment, but ABA is not, because it does not have B paired with last tape. And the language of a constraint is set of all satisfying assignment. So here there is only one variable x, and all satisfying assignment will be of the form AB raised to n, where n ranges over natural number. So that becomes the language of the constraint. And another kind of atomic constraint is relational constraint, where we can define relation between two terms. Term is nothing but a sequence of constants and variables. And this relation is definable using input-output automata. So I think most of you must be familiar with finite state machine, where we have finite number of states, transitions between them. If they are labeled by input as well as output, it's called transducer. Here is a sample example which has two states, one initial state which is indicated by arrow, one final state, and what it simply replaces A with B. The left side of the slash is the input, right side is the output. So it replaces A with B and B with A, and it accepts the string if it has even number of B's. So this is the simple transducer. And suppose our constraint is xy belongs to this transducer, or basically when we evaluate the assignment for x, if we run through t, then we get the valuation of y. So sample valuation is given here. If x is a b b, y will be b a a. And here the language of this constraint phi will be a two tuple words, because there are two variables. And formally defined as string constraint is formally defined as conjunction of both of this kind of string constraint, that is membership or relational constraint. It simply says that x has even number of a's, y has even number of a's, and X and Y are related by the transducer, what we had seen in the previous slide. So now, any constrained language, the most burning question is whether given a constraint, does there exist a satisfying assignment for that constraint? It's called satisfiability problem. And this string constraints are heavily used in sanitization of database inputs. There is this funny comic which shows that if we do not sanitize our database input, then it can lead to disastrous situation. Let's see some results, history about string constraint, what work has been done in this area. The satisfiability problem easily becomes undecidable for general string constraint because we can encode this famous undecidable problem PCP into the simple string constraint, that is XX belongs to R. So decidability is like whether given any string constraint, can we answer whether it has a satisfying assignment or not? That is the question, decidability. It is, given any constraint, we cannot, I mean, there is no algorithm which given any constraint will say if it is satisfiable or not satisfiable. So people have tried getting decidable subclasses for which the satisfiability is decidable. So one such subclass is straight line fragment. So a string constraint, if there is a dependency on, what is dependency here is that if we write x, y belongs to R, that means y is dependent on x, because to produce y, we should know the value of x. So if we do not allow cyclic dependency, that is like here there is cyclic dependency, x belongs to R, then that fragment is straight line fragment, and it is shown to be the satisfiability for this fragment was shown to be decidable, and future work has been done for that. Another well-known subclass is length preserving. So here the cyclic dependence is allowed at some extent, that is x1 depends on x2, x2 depends on x3, x3 depends on x1, like that. But the restriction is on relation, that relations are length preserving. So that is the meaning is that whatever the length of x1's valuation, the same length should be preserved for x2's valuation, and so on. So relations are like one to one or letter to letter. So now we will look at another problem, separability problem, which will help us decide satisfiability of some of the string constraints which are not from the known subclasses, that it's straight line fragment or length preserving fragment. This will help us decide satisfiability. So let's see what is separability problem. Given two constraints, phi1 and phi2, it asks, does there exist some separating language which separates L phi1 and L phi2? What does it mean is that there exists a set, superset of L phi1 and which is disjoint from L phi2. So if that such separator exists, then we are sure that phi1 and phi2 conjunction is unsatisfiable. That is, there is no satisfiable assignment for phi1 and phi2. Formally, if phi1 and phi2 comes from class C and separator comes from class S, it's called S separability of class C. So we in our one of our result, we have shown that any string constraint phi, given any string constraint, general string constraint, we can construct two straight line fragment constraint, phi1 and phi2, such that they are equisatisfiable, meaning that if phi is satisfiable, then phi1 and phi2 conjunction is satisfiable and vice versa. So if now for this phi1 and phi2, if we check for separator, if there exists a separator, then we are sure that phi1 and phi2 is unsatisfiable.
With respect to the separator and L phi 2, what you're asking the same question as you're asking for L phi 1 and L phi 2, that they are not overlapping or something, that's different. Is it the same question that you're asking for S and L phi 2 as you're asking for L phi 1 and L phi 2?
The question is about phi1 and phi2, that does there exist such S which is superset of phi1 and disjoint from phi2?
Yeah, I'm trying to understand why are you asking that question. Does it make it easy for you?
Yes.
Otherwise, I'm not understanding why this question is relevant.
So because in general, we do not know the answer whether if given any phi1 and phi2, if it is satisfiable or not. There are some fragments for which this answer is known. There are algorithms. For example, simply if xy belongs to R1, y belongs to R2, The first one, both are, there is no cyclic. But if we take conjunction of there exists cyclic
Okay. Okay.
constraints. If we can get separator, we can say that the conjunction is unsatisfiable.
Okay.
These are our results, which are done in collaboration with Parosh and Fauzi. We have shown that if the separator class is a regular language, then regular separability of string constraint is undecidable, as well as straight line constraint, it becomes undecidable. So we have now explored another separator class, which is piecewise testable language. Why we used this class is because this class is heavily used in language separability. There are multiple results about PTL separability of different kind of languages. In formal language, we have many different languages like regular language, context-free language, multi-push-down language, and so on. For all of them, this PTL separability is well studied. So for our usage also, we use help of it. And piecewise testable language is a Boolean combination of piece languages, which is of the form sigma star A1, sigma star A2, sigma star AN. So basically it says that there is a subword A1, A2, AN. And then such languages, if they are connected with union, intersection, negation, then it becomes PTL class. And we have shown that the separability is decidable for this class, but it uses, at some part it uses algebraic proof. So because of that, we could not extract the complexity here. So I'll show one part of this proof, which is basically encoding of solutions of straight line fragment to ordered multi-push down automata. So don't get afraid of these names. So first let's see what is it. So push down automata, maybe you know that it's a finite state machine with a stack as a storage element. So we can push and pop from those stacks. At the top of the stack, we can push and pop. Now MPA, so multi push down automata is where we have multiple stacks as storage element, and ordered multi push down automata is that the stacks, multiple stacks are there, they are ordered, and we can do the pop operation only from the non-empty stack, from the first non-empty stack, sorry. So because they are ordered, we can say that from the first non-empty stack, we can pop, but we can push in any stack. So that is ordered multi-push down automata. So I'll quickly go through this encoding. It's interesting to understand this. So suppose the constraint's general structure is like this. It's a conjunction of membership constraint as well as and conjunction of relational constraints. So let's say xi is our variable, ti our term, and straight line fragment has this restriction that xj appears in ti, then j is greater than I. So dependency is over higher index variable only. So xi is the output here, ti is the input. So xi is dependent on variables which are higher than it. So we will construct one ordered multi-push down automata which will satisfy ti xi belongs to ri. It uses linear number of stacks. So this is what we want, that initially we have suppose valuation of xi plus 1 to xn in our stacks. At the end of computation of AI, that is constructed OMPA, we want to get valuation of xi, okay, which satisfies ti xi belongs to ri. So this is how we'll go about it in phases. So in first phase, what we will do is that we will pop the contents from first n minus I stacks and push this contents in next n minus I stacks. Simple. And at the end, we will get reverse of each valuation in this second n minus I stacks. Now in the next phase, we will again pop from this n minus I stacks and push the contents in the last n minus I stacks. As well as during this process, we will also push the values of this variables if they are present in ti into this stacks, the third set of stacks. Okay, first we popped and pushed the elements in n minus I stacks, last n minus I stacks, and parallelly we have also updated this ti mod ti stacks, which will contain the input for to generate xi, because they are only dependent on variables which are higher than xi in the index. Okay. So this way we got the valuation of Ti in this third set of stacks. And now I think it's easy to understand that we will pop from this Ti stacks and run the transducer for Ri and get the valuation of Xi. And this valuation what we get is pushed into this stack, the fourth set of stack. So this will get us reverse of Xi which we wanted. And in the last phase, we will just pop from this stack and push into this stack. This will become Xi which we wanted. Okay. And this can be repeated for all the constraints, all the variables Xi which have relational constraint. And this kind of OMPA can be concatenated. Now we have seen that how to satisfy this constraint using OMPA, but we have not taken care of membership constraint. So now at the end of this OMPA construction, we will have valuation of x1 to xn in the stacks. So we will pop the stacks one by one, read whatever was there, and simulate the corresponding automaton for regular language and see if it actually belongs to that language. So at the end, we will have language, and while doing this popping, last popping, we will read hash in between when we jump from one stack to another stack. So at the end, what we get is that if V is satisfied by some satisfying assignment W1, W2, Wn, then the language of OMPA will contain W1 hash W2 hash Wn. And this is like if and only if. If OMPA contains this, then it should be a valuation of phi. So that is our result, that we first show that PTL separability of ordered multi-push down is decidable, then we encode the constraint solution to OMPA language, and then we show that the separability at both places is same. Basically, if formula are separated, then automaton are also separated. So why I discussed this is that the problem we started with was practical, but the solution required theoretical understanding, because we had to go through ordered multi-push down automata, encoding, and also like this proof of PTL separability. It uses other results from algebra. So it's like a problem will come from practical perspective, but to solve the problems, we might need a bit of other areas as well. Automata, logic, in theory I'm talking about, automata, logic, algebra. So this kind of practice will come from, or this kind of understanding will come from practice. We have to read papers, go into research, we talk to people. That way we will get an idea gradually. Yeah, I'll quickly talk. I'll not go into detail, but we have also explored another separator class called POS-PTL. So it is a positive Boolean combination of piece languages, and we have shown it to be decidable. So for that, we have very elegant proof which says that two languages are POS-PTL separable if and only if upward closure of one is disjoint from another, or if and only if downward closure of one is disjoint from another. It's quite simple. We have made it quite simple. So, and yeah, we have also defined another subclass of constraint. We call it right-sided SL constraint. So it is such that there are some independent variables and all other variables are directly dependent on it. And it can implement all straight line constraints with functional transducer. It is fairly practical subclass because it contains all functional transducers. And for this particular result, we have taken help from transducers, two-way transducers we have. So actually my PhD topic and my previous work was fully on transducers. So when this question came, it became somewhat like intuitive that we can use transducer for this to solve this problem. And we have shown that it is decidable in X space. Okay, then I'll quickly, due to time constraint, I will not go into detail of this proof. We can talk about it later during break if you want. So yeah, shifting gears. So now I'll talk about some industry application from formal verification. So I work in hardware industry, and there formal verification is largely used. So any product or design goes through product life cycle, including starting from whiteboard phase, architectural idea, microarchitecture logic, design, synthesis, silicon. And nowadays it has become like mandatory to get formal verification sign off for this part, that is design. And this design is done in hardware language like system Verilog. So there exists some tools, vendor tools, which can take input as this code, Verilog code, and there we can write properties which are based on linear temporal logic. The tool will take that property and actually check this question. This is like model checking is central question in formal methods. It asks, given design, I mean, does my design, does it satisfy the intent, that is specification? So the same problem is asked here in hardware industry, that given this design, does it satisfy architectural idea? So even after, I mean, there is lot of research in set solvers, model checking. After years of research also, there is always scope of improvement, because still our designs are not scalable by those tools. And we have to use abstraction technique to get the convergence, or sometimes we have to be happy with the bounded proof. So for that, I think this is where academia and industry, if they come together and try to get some solution or improve, for improvement there is always a chance. We saw this life cycle. So currently here the formal verification has become mandatory, but if we push it or do shift left, that is we can do formal verification here or here, then the issues which can be caught, that will not go into further cycle. So it will save a lot of time and human effort. So basically nowadays it has become, recently it has also started architectural formal verification. So for example, I'll give you a very basic example of it. It is very popular in protocols, cache coherency protocol. So if there are n number of caches, they all want to access memory, and there is this memory is guarded by some homing agent. So caches will send requests to home agent, and home agent will get the memory and give it to cache, or I mean do something such that cache will have access to it. So here again for architectural formal variation, it has challenges its own. So it does not have design available. So whoever is doing it has to model the design and then pass it to some model checker. Tools are still, I mean, some tools are not scalable yet. So if we go from this models are parameterized. So we have multiple different parameters, and number of caches, number of buffers, and so on. So if we increase the number of caches, sometimes it is not scalable, the proof will not converge. Since there are many parameters, there will be so many configurations. How many configurations to check? There are two issues. Like if there are many configuration we think, then we may not have time, deadlines are approaching, or it is not even feasible by a tool, because sometimes if we increase cache, it becomes non-convergent. So for that, if there is some mathematical intervention which says that we have to only verify this set of configuration, or if we can say that if we verify the system for 3 caches, we do not need to verify it for 4 caches. So there some mathematical abstract ideas can be used to, so those kind of problems are quite interesting there. So yeah, these are the problems in industry. So yeah, with this I'll conclude my talk. Thank you so much. I had uh, yeah, I was fortunate enough to work with very good collaborators, my guide, uh, and I wish all of you to have such wonderful journey. And thanks for inviting me. Yeah, any questions I can.
Thank you. This was a nice talk. So I have some background in programming languages and coding and so on. So I do some work in that space. So one of the biggest challenges that we find is more than verifying, even writing the specification compactly, right? That seems to be often as challenging as verifying.
Yes.
So you had, in your figure, you had two places where you said you can introduce verifiers, right? So
yeah.
so how do you think about specification problem here? Like, is it can
It
you
is one of the challenge because we do not have design available, so we have to write the code. Whoever is doing modeling should be confident enough that whatever model he has written or she has written should be what is intended to be. So yeah, there are various ways to formalize the specification itself using tables or diagrams. But at least in my experience, I have not seen any complete method. Tables are still formally, I mean, it is currently used and it's kind of formal because it's a complete thing. We can visualize it. But the diagrams, in my view, it is not, yeah, I mean, people say that it can be one of the good way to formally represent specification. Yeah, it is. So these two are formal representation for specification.
Thank you.
So I have an electronics background, and I know how to write Verilog code and everything. And we have been taught to use Cadence and Synopsys tools like that for verification. So right now, what we discussed about string constraints and all of that, I wanted to know: is this what is going on in the background of those tools during formal verification? Is this what goes on? Because we never understand what goes on in the back end of those tools.
Right. Yeah, they are all confidential things. I mean, even I am not from Cadence or Synopsys, so I don't know. But I suppose, yeah, that's what in the back end of the tool, there is model checking algorithms, set solvers, they are present there.
So my follow-up question is, formal verification in the hardware industry, where exactly is it used and what does one do to get a role in that?
Yeah, currently it is used at this stage to formally verify the design.
Correct.
And in most of the companies, it has become mandatory to do formal verification at this stage. And in some companies, it has also become like not mandatory, but it has started to do formal verification in this areas, that is architecture and microarchitecture phases. So yeah, I think your question was what to do for. I think understanding of logic is, in my view, it is required to solve this kind of problems. And yeah, that's linear temporal logic is also one of the thing which you can learn to get transfer.
Thank you, ma'am.
Thank you, Dr. Vrunda, for the fantastic talk. May I request Professor Purushottam to give a token of appreciation to Dr. Vrunda?
Thank you for inviting me. It's always nice to be back at IIT.